Welcome to the last talk of the day. There's going to be a poster session afterwards, and Mikhail Cuntz is going to tell us about Grassmannians over rings and subpolygons.
Thank you very much. I'm very happy to be here and for the opportunity to give a talk. Yes, and I'll say a little bit later about this picture. Let me first show you the big picture, an overview. So there are three main subjects in this picture, and I did maybe 15 years ago. I was interested in these Y-groupoids, which are invariants, which are associated to certain Hopf algebras, quantum groups, and a little bit like in Lie algebra, Lie theory, when you classify semi-simple Lie algebras, you have a classification of Y groups which appears automatically, very old result, and certain special Hopf algebras, which are called Nichols algebras, you will have a similar situation, and instead of having Y groups, we will have a little bit more general objects which are called Y groupoids. And a very important thing about these Y groupoids is its integrality. So among the reflection groups, you have those which are crystallographic, which have everything is acting on a lattice. So this is a very important thing for Lie theory, because you have these natural numbers which count something. So here in this special case here of the Y groupoids, when they appear as an invariant, you have the roots which are consist of exponents in the PBW basis of the elements. And maybe 12 years ago, we classified all the finite Y groupoids, and it turned out that they are related to simplicial arrangements. So we have simplicial arrangements in a lattice, which is a very special situation, and we could classify them completely in the finite case. And at that time, we already noticed that there is some, it looks a little bit like cluster algebra, where you have in a Y groupoid, you also have objects which are connected by involutions. And in a cluster algebra, you would have some clusters which are connected by mutation. It looks a little bit similar. And so we also talked to, the result was together with Istvan Heckenberger. So we went to Paris and talked to Bernard Keller, and we tried to find this connection, and it wasn't so clear. At least in the case of rank 2, and the Y groupoids are of rank 2, then there is a connection. So the reflection groupoids of rank 2, they would correspond to cluster algebras of type A in a certain sense. There's a link. But since then, I always was looking for a link in higher ranks. So rank 3 is completely different, and I never found one. And but now in the last years, I looked a little bit more precisely at cluster algebras, and and I also worked on arrangements, and in particular on arrangements which are defined on a lattice. So the corresponding matroids will have some additional structure. If you're on a lattice, you can, for example, encode the volume of, instead of only saying whether a determinant is 0 or not, you can also encode the volume of the vectors you are looking at, of the parallelotope spanned by the vectors. And last year, I found a connection between all these three domains. So, okay, so throughout the talk, maybe you should imagine a matrix like this. So everything is about a matrix. Maybe you already see what this matrix has as a special property. So except that it consists of integers. Okay. Yes, so you have this every consecutive 3 columns have determinant 1. And it's a very special type of matrix. So you have a determinant 1s everywhere here. And yes, but for the moment, maybe that's all. Now, we want to view this matrix in 3 different ways. So first, of course, it's a matrix. So, okay. So in the talk, I will have a rational matrix, but in fact, you can choose your favorite principal ideal domain and take the field of fractions. So this is a field of fractions of my favorite principal ideal domain, which is a ring of integers. Now we have a matrix with k rows and n columns. You can view this matrix as an arrangement of hyperplanes if you just say that every column is a linear form, which has a kernel. So we would have n hyperplanes. Or you can also view this matrix as a subspace of a k-dimensional space if you consider the rows of the matrix. So let's assume that it has dimension k. So every matrix is an arrangement of hyperplanes and a subspace. So if it's a subspace of Q to the K, it's a point on the Grassmannian. Yeah, Q to the N, sorry. Then it's a point on the Grassmannian. Okay, and to describe a point in the Grassmannian, you need so-called Plücker coordinates. What you do is in this matrix, you look at every square submatrix and at the determinant, and the determinants of all the square matrices within this matrix are the Plücker coordinates. Okay. Questions so far? Now, for k equal 2, so you have just 2 rows in your matrix. You can visualize such a matrix in a certain way. So we would draw an n-gon, and the labels of the n-gon are the columns of the matrix. So we have here 10 columns. And every edge and diagonal in this n-gon corresponds to a determinant. So if you take, for example, this 4 and 9 would be the matrix consisting of the column 4 and 9. And then we can attach to each diagonal and edge the determinant. And then we would see, in the case of k equal 2, you have a relation between diagonals and edges, which is such a Ptolemy relation. So whenever you have a square, here 1, 4, 7, 9, for example, then you always have, so these are determinants. So this times this plus this times this is equal to the product of the orange ones, which is here. So P17 and so on. So this is a Plücker relation for k equal 2. If you do this for k equals 3, then every determinant would be a triangle, because you have 3 columns for each square submatrix. And this is just a representation for telling that. So this is a product of this determinant times this determinant minus this one times this one, and so on. And this should be 0. So you have a quadratic relation given by products of determinants. And it's not too difficult to see. In general, the Plücker relations are given by quadratic relations, which look like this. This is easy to see. It is some sort of Laplace formula. So you look in this matrix and compute determinants. And well, and these relations are the relations defining the Grassmannian. So the coordinate ring of the Grassmannian is a polynomial ring, which has a variable for each possible determinant, and satisfying the relations. Okay. Now, what we can do is, what we do when you have a cluster algebra, and some people consider freeze patterns, and what they do, they specialize the variables in the cluster algebra to some number. And let me call this a specialization. Choice of a point here, if you want. So a homomorphism of this coordinate ring to the rational numbers. And then since we now only consider the determinants, it's not clear a priori whether we have what type of matrix we find which produces exactly these determinants. So here I say, well, these determinants should be equal to certain numbers. And now I want to find a matrix such that these determinants become that these numbers become determinants of square submatrices of this matrix. And let me call this a representation. So it's not the same. So if you look for a matrix over a field, then it's not too difficult to see that it always exists. But since we will be interested in integer entries, it will be a little bit more subtle. Okay, so since I don't know how much you know about cluster algebras, just an example here. So for k equal 2, you have a structure of a cluster algebra, which is the following. So the variables are diagonals and edges in this n-gon. And the edges, I have in red here, I don't know if you can see it, are frozen variables. And the other diagonals are the other variables. And the cluster consists of a triangulation of this n-gon by non-intersecting diagonals. So the cluster variables are, for example, here I chose a triangulation non-intersecting diagonals, and then all the edges and diagonals here would correspond to cluster variables. And then in a cluster algebra, which is commutative algebra generated by all these cluster variables, you have, when you have one cluster, you have a mutation which produces a new cluster and so on. And here in this special case here of cluster algebras of type A, the mutation corresponds to a flip of a diagonal. So you would use a square somewhere which consists of two triangles, and just take the diagonal and flip it. And well, you replace this variable by this one, and using the Plicker relation, you can compute a new variable, because you know this times this is equal to this times this plus this times this, and you get a new variable. Each time you mutate, you get a new variable, and you can continue. And at the end, you can get all the diagonals if you want, starting from an original cluster seed. So this is mutation in a very nice example. Here in this case, you have finitely many clusters, which correspond one-to-one corresponds to this, the triangulations. So they're counted by Catalan numbers. So this is maybe the nicest example. And a Fries pattern would be, so instead of just taking variables in the cluster algebra, you would fix some entries. So you would specialize these variables to numbers. And what you can do, if you specialize all the variables in one cluster to 1, then you automatically get that all the other cluster variables would be positive integers. There are two reasons. One is the positivity theorem. I'm sorry, I cannot cite all the people who participated in this project, but you can prove that if the variables are in a cluster are positive, then all the variables will be positive. And the other one is this Laurent phenomenon. So in the denominators of the functions you will get are monomials, and the numbers in your original cluster. And since in the original cluster you chose everything to 1, you will have a 1 everywhere. So you will never get a rational number if you start with a cluster. You specialize everything to 1. Okay, so we can do this. We choose our favorite triangulation of an n-gon. We specialize every diagonal edge to 1, and then we compute every other diagonal and edge using the Plicker relations, or Ptolemy relations in this case. And it turns out that we get what is called a Fries pattern. So this is a matrix. In this matrix, well, in the entry ij, the entry ij corresponds to the edge or diagonal ij. So we have, since we have here, okay, so for example, the zeros here correspond to the determinants ii. So if you take 2 times the same column, you get determinant 0. If you take ii plus 1, then you will have a frozen variable, which is always 1. So you get this diagonal of 1s here. And the next green diagonal here, these are the ii plus 2 determinants. They are called the quiddity cycle of the Fries, because you can also complete the picture using this green diagonal. Because what is not too difficult to see, if you draw this matrix, that every 2 times 2 determinant is 1. So every 2 by 2 matrix, which are of adjacent numbers, has determinant 1. And what you can also see, which is not too difficult, is every 3 by 3 matrix has determinant 0. And this is something we call tame in this case. And whenever you specialize a cluster algebra cluster to some numbers, and you produce all the other entries here in the Fries, you automatically get that the 3 by 3 determinants are 0. That is not too difficult to prove. And what you also get is in this Fries pattern. So in particular, you get automatically a representation of this the specialization you chose. So you get a matrix here in this orange box, and this matrix is such that, well, the determinants of ij are exactly the values on the diagonals and edges ij. Questions? I forgot, this was proved first by Conway and Coxeter. So I think Coxeter introduced this concept of Fries patterns, but this was long before cluster algebras were found. So this was maybe in 72 or something like that. And in a nice paper, Conway and Coxeter, they classified these. So the classification is not too difficult. So what you do is, so the Fries pattern, in fact, is a diagonal of zeros, then a diagonal of ones, then you have your favorite natural numbers, and then you fill the picture just by adding the next number which produces a determinant 1. So for example, here you have to put a 3 because 4 times 1 minus 3 is 1. And so this green diagonal will determine everything. So it's overdetermined because in fact you have 3 degrees of freedom less, but the cluster has three variables less. But, okay, and what you can easily see, I don't have enough time to prove it, but the green numbers are just the number of triangles at every vertex. So here you have 1 triangle, you have 2 triangles, you have 4 triangles, 1 triangle, 2, and this is the first non-trivial diagonal, which is a green squidity cycle. So the number of triangles at each vertex here is exactly the determinant of I plus 2 corresponding to the vertex. Okay.
Ask something? Sorry, very quickly. If you rotate the polygon, does it mean like lifting up the fixed pattern?
Yes, you just so it continues in both directions infinitely, and it's just a shift. Yes. Yes. Mm-hmm. Yeah. Yeah. Okay, and this is also so the Y groupoids of rank 2. They have several root systems. So one fixed Y groupoid will have many root systems, and the root systems are pairs of consecutive rows. So this is a root system here of a Y groupoid, and the next pair of rows is another root system of the same Y groupoid, and so on. But I don't want to say this today. Okay, now what I did a year ago is to look at the case where k is equal to 3 and more. And first, there isn't a good definition of, well, there are many definitions of SLK freeze pattern. So this is an SL2 freeze pattern because you have a SL2 condition for the 2x2 matrices. But in general, I would say an SLK freeze pattern would be visualization. Sorry. Such that the psi of when you take a square so a variable t I1 to ik, and then this should be an integer positive, and you want to have a consecutive columns should give a frozen variable which would be 1. So if you started in label I plus 1, and so on, okay, I plus k minus 1 should be equal to 1. This would be an SLK freeze pattern, and you want to understand SLK freeze patterns, which is not so easy, and there are many nice correspondences between other types of so for k equals 3, for example, you find certain cluster algebras of type E, E6, E7, E8 appear, and so on. So it's very interesting what you have here. And I mentioned before the problem of representations. Well, it's not really a theorem, but let me call it a theorem because it's useful. So if you have a principal ideal domain, and you have a specialization of the coordinate ring VKN. Such that all the entries are non-zero. And then it's not too difficult, it's not trivial, but it's not too difficult to prove that psi has a representation. So there is a matrix, such that these numbers we have chosen are determinants. So if R is a field, then it's easy. But if it's not a field, then you need to look at the GCD. Let me call it delta. So the GCD of all the numbers psi of 1 I. If you take this GCD, then you can produce, and now you recursively construct a representation by you get a representation where you put just this GCD in the first column, and then the remaining part, the problem which is one smaller, and then you can continue on. So you have to be a little bit careful and get this part here. And so this is a representation of psi, and then now we do induction. So that there's some details here, but in principle, you have to look at GCDs, and it's a quite important thing that you are in this principal ideal domain. You're not allowed to do linear algebra all the time like you want. You have to, and this makes things very complicated. And here's an example where this can be a problem. So for example, let me look at A23. So I specialize the following way. So this is a classical case like here, but I want to have I want to have a 2x3 matrix such that the first two columns give determinant 3, and same for the columns 2 and 3, and the columns 1 and 3. So they all have to be 3. So the picture would be, we have an n-gon, which is a triangle, and every edge should have value 3. So this is not the convex freeze pattern, because this frozen variables, if they were, then they would have to be 1. And now we have a new phenomenon, which is which you don't have in, if you look at here, where you have representations. So one would be, for example, this one. We choose this matrix. So of course here we determinant is 3. So this determinant is 3, this one is 3, and all the 2x2 determinants are 3. But I could also take this matrix. Also works. And there is a big difference between the two examples, because here you have a column where the entries are not co-prime. You have here the GCD of these entries is 3. And here all the columns have the property that the GCDs are 1. So the difference is, in fact, so we have the same metroid if you want, but you have additional information, because you have the information of the volume of certain vectors and pairs of vectors and so on. So this vector here has volume 3, you have volume 1, and here all of them have volume 1s, which is completely different. So this extra information is what, for example, Luca Mucci and Roberto Pagaria and some others called an arithmetic metroid. So it's a metroid with an additional function which associates to this determinants the volume of the corresponding columns. Okay. So this is important, because now if we start with a specialization and we want to find a representation, we can sometimes we find such a representation here, or maybe we want to have this type of representation. The reason is, since we want to have a freeze pattern at the end, we want to have that the columns have co-prime or co-prime entries, because otherwise we cannot have a determinant 1. And the same for SL3 freeze patterns. We will need that the columns of our representation all have co-prime entries. Yeah? Now, there's an interesting question. So, which was asked by Peter Jorgensen a few years ago. Take an n-gon, put some specialization, where all entries are specialized to natural numbers. Is this contained in the bigger convex freeze? So or the other way around. So you take a convex oxidative freeze, you cut something away, you just remove parts. If you remove parts, then automatically you still have the pre-correlations because you have the same relations as before. But what do you get? So for example, it's not possible to get the triangle 2, 2, 2 within a freeze pattern. And this is what's a little bit strange. So we looked at this in more detail and we found this first result. So a triangle ABC, so the triangle has only 3 edges, and ABC appears as labels of a triangle in a oxidative freeze if and only if. So first you need that the GCDs of AB, BC, and AC coincide. We call this a GCD condition. And the second condition is a little bit strange. So either all of them are odd. So nu2 is a 2 valuation of the integer. Either they are all odd or there are at least 2 different 2 valuations. And we didn't really understand why, but we found a proof. So the proof works with this diagonals and n-gons, and it's quite complicated because you have to you start with a triangle and you have to construct a freeze pattern which contains this triangle in the case when these conditions are satisfied, which is not so clear. And then I had a master student and I asked him, what about squares? And he found an example which looks like this. So you have the edges on the border, you have 3s. And then here you can have a 3 and a 6, and you will have the correlation is 6 times 3, which 18 is 9 plus 9 is okay. So this is an example of a freeze pattern, and it does not appear within the convex oxidative freeze, which was a result of this but was one part of his master's thesis. And so I looked at this together with Thorsten Holm. Sorry, I forgot. This is together with Thorsten Holm and Peter Jorgensen. And we found out there is a generalization of this. So if you have now let me formulate it like this. So a specialization C of A to N to positive integers appears as a subpolygon of a convex oxidative freeze if and only if we have the same GCD condition as before. Every triangle satisfies this co-prime thing here as GCDs. And now the interesting thing is for every prime number less than N, now we consider P plus 1 subpolygons of C. And within these P plus 1 subpolygons, either none of them is divisible by P, or they have at least 2 different P valuations. Yes. And this is a little bit strange. So we prove this, and the proof is very difficult. So you have to, and there's several pages of technical details, how to add something in a freeze and not, and so on. It was a very nice result. We were very happy, but we never understood at this point why P plus 1 and why every prime, and it's a little bit strange. And when I looked at this last year, I had this new view with these representations. And so I noticed that in fact this P plus 1 comes from the fact that the projective line over FP has P plus 1 points. And now for higher K, what you get is an analog. So this is the theorem for higher K is you have to split it into 2 parts. First, you have to characterize those specializations which have a representation where all the columns have co-prime entries. So this is a quite complicated theorem. So you have to, now R is an arbitrary principal ideal domain, but you can imagine it's integers. And if all the entries in the specialization are non-zero, then and you look and you take the prime factorization of the GCD of the entries, then you have to look at all these primes, and then again you have a GCD condition with now it's formulated with ideals, but it's the same as before. And the second one is very nice. You count the number of points in the projective space for each prime. And now you look at all the subsets of vertices which have this size, and you look at the valuations of the corresponding prime on this subset. So you have just a straightforward generalization if you want, but the proof is completely different. And this is nice because I have a completely new proof of this other theorem, which is not trivial. And the reason is now we have coordinates, we have these representations, and the important thing here is really this here that the entries in each column have, so each column has volume 1, so the entries in the column are co-prime. And so this characterizes all specializations which which have a representation where the columns are occupied. The second step is to produce an SLK freeze pattern which contains such a representation. And this is the second theorem. So if we have a representation as we found before, in the special case, and now we have to restrict to the integers because we need positivity. We want to have only positive entries in the freeze, and for a principal ideal domain in general, we don't have positivity. And now if we assume that all these determinants are positive, then we can extend it to an SLK freeze pattern. And this was also a nice problem, and it's not trivial. What you have to do is, you can imagine you have your you have computed a part of your n-gon, which will be the freeze pattern at the end, and you have to add something new. What you have to find is within this cone here. So this would be, for example, a three-dimensional cone. You have in the lattice, you have some points here. You have to find a point here, which extend this in a nice way. And this it took me some time to find it because so if you're too close here, you have problems. If you so it's not so clear how to argue to get this point, but apparently it seems to work. And then it's not unique. You have several different ways to extend it to a freeze, but in the end, you can prove this, and then we get the same equivalence as for k equal 2. Now there is a thing which is maybe interesting for the audience here, and I want to advertise. So I'm also looking at this together with Patrick Wegener. So what you can do, and so in the same subject, you could so these cluster algebras I didn't say it, but this coordinate ring of the Grassmannian has a cluster algebra structure, but it is much more complicated than for k equal 2, because for a k equals 3 and higher, you would have infinitely many clusters for most values of n. And well, a finite set of clusters corresponds to non-intersecting families of k-gons in whatever this means. And then there are infinitely many others, which you have to describe with quivers if you want. And what you can do is, well, if you specialize all the variables of a cluster to 1, you would get a freeze pattern. But if you specialize the variables to 1 and -1, then you could, well, the law of Feynman and so on, it will tell us that you could get a 0 somewhere, which would mean that a certain determinant would be specialized to 0, and then you will get an interesting metroid structure in the representation. So so in particular, for example, here for k equals 3, if n is equal to 9, and I choose exactly these signs here for these triples of vertices in my n-gon, then I get a representation, and this representation turns out to be the root system of type B3. It's a little bit strange observation. So, so my question is, do we get all the root systems of Y groups by specializing a cluster in this cluster algebra to 1 and 1s1s? So what you need, for example, is so you can ask this question with several conditions. For example, you could request that every consecutive 3 columns have determinant 1. So the first question would be, is there an ordering of the root system such that consecutive k roots have determinant 1, which is not completely clear. And then, of course, there are many other questions of this type you can ask here. And I think first experiments show that it's not always possible. I did some experiments also for the root system of Y groupoids. There I found some which possibly do not work. So it's even strange that if you choose a cluster and specialize to 1s and -1, that you get some nice simplicial arrangements at all. So you find, I don't know, simplicial arrangements with 25 lines just by choosing the right set of signs on a specific cluster. And I don't understand yet what this means. But, I think it's a very nice observation, and I wanted to get it. One of the reasons why I'm here this week, I wanted to advertise a little bit for looking at these clusters, and for the cluster algebras in particular, which are not a finite type way, because you have these infinitely many clusters. Okay.